Hi algebra students. So on this lesson we are going to be adding and subtracting radicals. So far we have simplified and multiplied radicals, we have divided and rationalized and simplified radicals, and now we're going to add and subtract. And so adding and subtracting radicals is a lot like adding and subtracting variable expressions, where you can only combine like terms. With radicals, you can only combine like radicals. And so if we want to think about a similar example back from first semester in algebra or even a previous year, you might have something like 3x plus 5x, right? And when you combine these, what you're really doing is you're adding the 3 and the 5. So we know that we're going to get 8x, but what's happening in order to do that is you really did 3 plus 5 and then times x, right? But we normally did that part in our head. So when we look at the rule here, here's the generic rule. We're combining the outsides, x plus y, and we're keeping that radical the same, just like here. We kept the x the same, that didn't change. Or here, 3 plus 5 on the outside and keep the root 2. So 8x versus 8 root 2. Okay, so now we'll apply that rule. So we're looking at 2 root 7 plus 6 root 7. So we have an example up here. And so what we're going to do is we're going to combine our 2 and our 6. If it helps you to write it out, go for it. But I won't after probably this example. So we're going to combine those outside numbers. And then we're going to keep the root 7. So what we really end up with is 8 root 7. So on the next one, it's very similar. Go ahead and try it super fast. Just pause real quick, and then you can look at your final answer. So I'm doing 3 minus 9 is going to be negative 6, and keep the root 2. Okay, our next example is very similar. We just now have a variable in the radical instead of, say, a root 7 or a root 2, but we'll work the same way. We'll combine our outside numbers, 9 plus 11, to get 20, and then keep your root x. So just like a regular x would be, we wouldn't change it. We're not changing the root x. So you're only adding or subtracting the coefficients. So on the next example, go ahead and write it down and then try it. Pause if you need to. Okay, so combining 9 minus 4, you should get 5 and keep the root w. So our next example is similar, but if you take a look at this, we have two radicals and they're not the same. And so in order to combine our like radicals by adding or subtracting, we actually have to have like radicals. What that means is we have to have them the same number under the root. And so in order to do that, what we can do is we can simplify, just like we've done a million times. We can do a factor tree for 12. Okay, so 12 has a pair of 2's and a loner 3. Remember, the pair comes out, the loner stays home. And then don't forget, bring down minus root 3. Now we can combine, because we have root 3 and root 3, so we're going to say 2 of them minus 1 of them. Remember that there's an invisible 1 here, if you need that. So 2 minus 1 is 1, so we just have a root 3 remaining. All right, so same thing on the next one. We need to get matching radicals here. We've got a root 10 and a root 40. Root 10 is fully simplified, so we'll have to fix root 40. So I'll do a little factor tree. So 40 is 4 times 10. 4 is 2 times 2. I wanted the 10 in there, so that's actually really good. I want that to be my loner. And then the 2 will come out. So we'll rewrite this. We'll bring down the 2 root 10. We haven't changed that. And then here, don't forget about this 7. So I brought down the minus, and then it's going to be that 7 times the 2 from here. And then all root 10. The 10 stays in. Remember, loner stays home. So then from here we can say we have 2 root 10 minus 14 root 10. Okay, well 2 minus 14 is negative 12. And we keep the root 10. For example 7, it's very similar, but now we have a variable included. So it's just like when we first started simplifying with variables. That's going to stay there and it's okay. So here I'm noticing I have a perfect square. If you don't notice it, just do a factor tree. You'll see 2 3s. So you can always do that. And you'll notice, okay, they both come out, or the single 3 comes out. The y has to stay in. So this is going to be 3 times the square root of y. I'll bring down my plus. Then over here, I need to have just a root y underneath. And then I'm also noticing, well, 16 is a perfect square, and the square root of 16 is 4. So I'm going to pull that 4 out and keep root y. Otherwise, you could have done your factor tree of 4 and 4. Okay, either way. Now we've got our like radicals, so we can say 3 root y plus 4 root y is 3 plus 4, 7 root y. So go ahead and write this next one down. Once you have it written down, then please pause the video and I want you to try it out on your own. These are not perfect squares, so it's not just going to be an integer and then root y. So you will have to do a little factor tree for the 24 and the 54, and you'll keep y in the denominator. Press pause, try it out on your own, and then check back in. Okay. So I did little factor trees for my 24 and my 54, and when I did that, I boxed the y so that I wouldn't forget it. And we'll see that we have a pair of 2's that will come out in front, and the 2 and 3 and the y are all loners staying home together. The 3 here comes out, the 3 and 2, or if you recognize that you had a 6 over there, that and y stay in. Remember, everything that stays in gets multiplied. If you have more than one thing coming out, that gets multiplied. So then we have 2 root 6y and 3 root 6y. We'll combine our 2 plus 3, getting 5, and keep the root 6y. Take a look at example 9. So this one for sure does not have like radicals, and we have to do some rationalizing. So that's the first step. And the first step on all of these, if you've noticed, is simplify your expression first, then look for like radicals to combine. So on this one, I'm going to simplify it by multiplying times root 3 over root 3. I'm not going to do anything to this one. It's already in its simplest form. So I'll bring that one down, root 3. Then over here, we have plus, right? Bring that down. And so then in the numerator, 2 times root 3. And then in the denominator, 3. Okay, because 3 times root 3 is 3, and that's from the previous lesson. So now we're closer. We've got our root 3 and our root 3, but we don't have common denominators. So now it becomes a fraction problem. So we have a 3 in the denominator 3 here. We want a 3 in the denominator here. So let's multiply by 3 over 3. Now we have a common denominator. So now we can add these together. So we're going to say, adding across the top, 3 plus 2 root 3. So that's going to be 5 root 3 all over that common denominator of 3. If we could simplify here, then we would have to. Our last example is very similar. So go ahead and challenge yourself. I know this last one wasn't super easy because we have to rationalize and deal with fractions. This one's going to be similar, but try it out. Really challenge yourself. So go ahead and hit pause now, and then you can play it back, and if you need to go through it, you can go through it again. So the first thing that I did is I multiplied my 1 over root 7 by root 7 over itself to rationalize this. From there, I ended up with root 7 over 7. I brought down my root 7 here and my minus. Then I had, if we just cover this part up, then I have root 7 minus root 7 over 7. So I didn't have common denominators there, which I need. So that's why I multiplied here by 7 over 7 to get a common denominator. Now I've got 7 in the denominator. I'm going to keep that. And I had to subtract. I remember that there's an invisible 1 here. So I said 7 minus 1 is 6. Keep the root 7. Keep the common denominator 7.